This is another of the gas laws, and what we're going to do is we're going to see how the temperature affects the volume of a gas that is trapped. Now what we've got is a very delicate piece here. If you can see, we've got a capillary tube that's sealed off at the bottom, so it's just level with the 10mm mark. And up here we've got a bead of sulphuric acid, and what that does is it absorbs moisture. So what we have here trapped underneath up to about the 32mm mark is we've got a bead of dry trapped gas, and at the moment that's trapped at the temperature of 23 degrees, which you can read off the thermometer there. What we're going to do is I'm going to take it through a fairly high temperature to start with. Okay, again, for safety wise this is good, and you'll see why. Don't worry, we'll become clear on the side of the glass in a moment. As we fill it up, there we go, it's starting to float. If the trapped air got too big, what it would do would shoot the bead of acid up. So it's rising ever so slightly. Temperature is still obviously rising inside the tube, it's rising inside the thermometer still, and you can take your reading off that. It's looking to be about steady now. Okay, so if we assume that it takes the same time to get through the capillary tube, which is very thin, as it does to get through the Pyrex glass on the thermometer, the thermometer is looking steady, so you can take a reading there. You had a reading at the beginning, and what we're going to do is change in stages the temperatures in between. Okay, so take your length of gas there, you take your reading, and you can always freeze the video to take your readings. Okay, so I've just added some cold water and it's sinking down. You can see the gas contracting. You can also see the bead in the mercury thermometer contracting, and still dropping, still dropping. I'll just stir it around with that to make sure the water is nice and even in temperature, because it's surprising how you can get hot spots and cold spots in it. Okay, the thermometer is steady now. Please notice it's not exactly on the bar, so again, try and estimate what the reading is to the nearest value that you can. You know, could you get to a 1/4 degree, 1/3 of a degree? Obviously it's a short thermometer, so it could be in the same slot, but there we go. Okay, so we'll cool it down a bit more and we'll get a few more readings. Okay, it's dropped about another 5-6 degrees, somewhere in that region. So again, take your reading for your volume and take your reading for your temperature. So next reading, steady on the thermometer and looking pretty steady on the gas as well. Okay. Okay, so we're cooling down, starting to get towards room temperature now. Bit of bead there. Starting to get towards room temperature, and your volume is starting to get back to where it was. Okay, so steady there. Yeah, well, that's steady, so you can take your reading and just add a bit more cold water, so it's a bit more real time. And again, you can start to see the thermometer drop, not dropping a lot, because once you start getting towards the original room temperature, then your rate of cooling slows right down. Okay, we get really cold water now. Okay, I've just dropped a bit more cold water in. Not getting much change in the gas now. The temperature has steadied, so that's not changing. And again, if this was a real experiment with you doing this in the lab time, you'd probably be waiting for a good minute to make sure the temperatures are settled and the gas volume is settled. And of course repeating the readings, but we're not going to do that just because we've got a lot of videos to record here. And just cold water to finish off. So temperature's dropping on the thermometer. There we go. Not dropping rapidly again. And again, trying to see without any parallax, looking directly at the ruler. That's where you're going to be able to get your reading. So temperature is steady. That's going to be our final reading. So you will see the last three volumes are very, very similar. You'll need to make sure that you look at those closely, try and get them to the nearest millimetre or so. Sorry, the nearest half degree or so would be ideal. Also note source of error. The volume right at the bottom, the volume of the gas that's trapped, is pointed, so it's not totally square. It does go a bit below the 10, and it tapers up and is full width at around about 11 millimetre mark, but you know, that's the best we can do. So final reading, plot the temperatures along the x-axis because the volume depends on the temperature, so that dependent variable is always going to go up the vertical axis. And if you plot this back, see how much this goes down with temperature. So at what point would the temperature be so low that all of that volume has squeezed up? All of the gas particles are basically in contact and sat still at the bottom of your little volume. Okay, when you get your results then, plot them on temperature on the x-axis because the volume will depend on the temperature. If you plot the volume up the side, then you can see how that drops with temperature. Draw a large scale like this. Okay, you do not have to start at 0 degrees. It could be, for example, I don't know, 15, whatever's convenient to fill the size of paper. And what you can do is, with this, you can plot a really good line of best fit. I'll do my best with that one, that's a bit rubbish. But you can find out how much it takes for the volume to drop by, say, 10. And then what you can do is realize you have to drop 40, so that will be 4 times longer. So you can do a scale, similar triangles, just take it all the way down. How much is that size compared to that one? Therefore you can do how much is that drop in temperature compared to the full drop in temperature to reach the 0 axis, to reach 0 volume. Okay, don't go, well, I know it's in Kelvin and so I'm going to plot it in Kelvin, because your data is going to be right up here. It's going to be tiny. You're never going to draw a line of best fit through those because the dots are so close together. So therefore your line of best fit will be so varied it won't work. Okay, so nice big graph with a good line of best fit, not like mine. Find the gradients and either use y equals mx plus c or similar triangles, big triangle, little triangle, to work out at what point in temperature does this volume reach 0. And that will give you an estimate for absolute 0. You may be way off if you get it anywhere between about 200 and 350. That's pretty good. The true value is 273.15. If you want to find percentage uncertainty, that will give you an idea of how well that experiment works. Okay, try it and show me your graphs.